Hi, welcome to Supervised Learning with scikit-learn. Here you get a chance to grow your machine learning skills with scikit-learn and discover how to use this popular Python library to train models using labeled data. In this course, you'll learn how to make powerful predictions, such as whether a customer will churn from your business, whether an individual has diabetes, and even how to classify the genre of a song. Using real-world datasets, you'll find out how to build predictive models, tune their parameters, and determine how well they will perform with unseen data. This course consists of 4 chapters, which are classification, regression, fine-tuning your model, and lastly, pre-processing and pipelines. In this video, having trained models, now we will learn how to evaluate them. In this chapter, we will be introduced to several metrics along with a visualization technique for analyzing classification model performance using scikit-learn. We will also learn how to optimize classification and regression models through the use of hyperparameter tuning. In the first part of this video, we'll learn how to test the performance of our model and what algorithms can be used to test the model performance. Thinking back to classification problems, recall that we can use accuracy, the fraction of correctly classified labels, to measure model performance. However, accuracy is not always a useful metric. Consider a model for predicting whether a bank transaction is fraudulent, where only 1% of transactions are actually fraudulent. We could build a model that classifies every transaction as legitimate. This model would have an accuracy of 99%. However, it does a terrible job of actually predicting fraud, so it fails at its original purpose. The situation where one class is more frequent is called class imbalance. Here, the class of legitimate transactions contains way more instances than the class of fraudulent transactions. This is a common situation in practice and requires a different approach to assessing the model's performance. Given a binary classifier, such as our fraudulent transactions example, we can create a 2x2 matrix that summarizes performance called a confusion matrix. Across the top are the predicted labels, and down the side are the actual labels. Given any model, we can fill in the confusion matrix according to its predictions. The true positives are the number of fraudulent transactions correctly labeled. The true negatives are the number of legitimate transactions correctly labeled. The false negatives are the number of legitimate transactions incorrectly labeled, and the false positives are the number of transactions incorrectly labeled as fraudulent. Usually, the class of interest is called the positive class. As we aim to detect fraud, the positive class is an illegitimate transaction. So why is the confusion matrix important? Firstly, we can retrieve accuracy. It's the sum of true predictions divided by the total sum of the matrix. Secondly, there are other important metrics we can calculate from the confusion matrix. Precision is the number of true positives divided by the sum of all positive predictions. It is also called the positive predictive value. In our case, this is the number of correctly labeled fraudulent transactions divided by the total number of transactions classified as fraudulent. High precision means having a lower false positive rate. For our classifier, this translates to fewer legitimate transactions being classified as fraudulent. Recall is the number of true positives divided by the sum of true positives and false negatives. This is also called sensitivity. High recall reflects a lower false negative rate. For our classifier, it means predicting most fraudulent transactions correctly. The F1 score is the harmonic mean of precision and recall. This metric gives equal weight to precision and recall, therefore it factors in both the number of errors made by the model and the type of errors. The F1 score favors models with similar precision and recall, and is a useful metric if we are seeking a model which performs reasonably well across both metrics. Links to web pages and datasets used in the upcoming slides are given in the description of this video. To get started, first download the latest Python from the official website you can see in this screenshot. Next, you need an integrated development environment, IDE. I would recommend using PyCharm Community Edition, which is a Python IDE, but you can also use any other tool of your choice which supports Python development. After downloading PyCharm, install it and create a new project with configurations you can see in this screenshot. Using our churn dataset, to compute the confusion matrix, along with the metrics, we import classification report and confusion matrix from sklearn.metrics. We instantiate our classifier, split the data, fit the training data, and predict the labels of the test set. We pass the test set labels and the predicted labels to the confusion matrix function. We can see 182 true negatives in the top left. Passing the same arguments to classification report outputs all the relevant metrics. It includes precision and recall by class, 0.6 and 0.55 for the churn class respectively, which highlights how poorly the model's recall is on the churn class. Support represents the number of instances for each class within the true labels. It's time to introduce another model, Logistic regression. Despite its name, logistic regression is used for classification. This model calculates the probability, p, that an observation belongs to a binary class. Using our diabetes dataset as an example, if p is more than or equal to 0.5, we label the data as 1, representing a prediction that an individual is more likely to have diabetes. If p is less than 0.5, we label it 0 to represent that they are more likely to not have diabetes. Note that logistic regression produces a linear decision boundary, as we can see in this image. Using logistic regression in scikit-learn follows the same approach as used for other models. We first import logistic regression from scikit-learn.linear model. Next we instantiate the classifier, split our data, fit the model on our training data, and predict on our test set. In this practical we use the diabetes dataset you can download from the link given in description. The default probability threshold for logistic regression in scikit-learn is 0.5. This threshold can also apply to other models such as KNN. So what happens as we vary this threshold? We can use a receiver operating characteristic, or ROC curve, to visualize how different thresholds affect true positive and false positive rates. Here, the dotted line represents a chance model, which randomly guesses labels. When the threshold equals 0, the model predicts 1 for all observations, meaning it will correctly predict all positive values, and incorrectly predict all negative values. If the threshold equals 1, the model predicts 0 for all data, which means that both true and false positive rates are 0. If we vary the threshold, we get a series of different false positive and true positive rates. A line plot of the thresholds helps to visualize the trend. To plot the ROC curve, we import our OC_curve from sklearn.metrics. We then call the function ROC_curve. We pass the test labels as the first argument, and the predicted probabilities as the second. We unpack the results into 3 variables: false positive rate, FPR, true positive rate, TPR, and the thresholds. We can then plot a dotted line from 0 to 1, along with the FPR and TPR. To produce a figure such as this. This looks great, but how do we quantify the model's performance based on this plot? If we have a model with 1 for true positive rate and 0 for false positive rate, this would be the perfect model. Therefore, we calculate the area under the ROC curve, a metric known as AUC. Scores range from 0 to 1, with 1 being ideal. Here, the model scores 0.82. We can calculate AUC in scikit-learn by importing our OC_AUC_score from sklearn.metrics. We call our OC_AUC_score, passing our test labels and our predicted probabilities, calculated by using the model's predict_proba method on feature_test. As expected, we get a score of 0.82. Now that we know how to evaluate model performance, let's explore how to optimize our model. Recall that we had to choose a value for alpha in ridge and lasso regression before fitting it. Likewise, before fitting and predicting KNN, we choose n_neighbors. Parameters that we specify before fitting a model, like alpha and n_neighbors, are called hyperparameters. So, a fundamental step for building a successful model is choosing the correct hyperparameters. We can try lots of different values, fit all of them separately, see how well they perform, and choose the best values. This is called hyperparameter tuning. When fitting different hyperparameter values, we use cross-validation to avoid overfitting the hyperparameters to the test set. We can still split the data, but perform cross-validation on the training set. We withhold the test set and use it for evaluating the tuned model. One approach for hyperparameter tuning is called grid search, where we choose a grid of possible hyperparameter values to try. For example, we can search across 2 hyperparameters for a KNN model, the type of metric and a different number of neighbors. Here we have n neighbors between 2 and 11 in increments of 3, and 2 metrics, Euclidean and Manhattan. Therefore, we can create a grid of values like this. We perform k-fold cross-validation for each combination of hyperparameters. The mean scores for each combination are shown here. We then choose hyperparameters that performed best, as shown here. Let's perform a grid search on a regression model using our sales dataset. We import grid search CV from sklearn.model_selection. We instantiate k-fold. We then specify the names and values of the hyperparameters we wish to tune as the keys and values of a dictionary, param grid. As always, we instantiate our model. We then call grid search CV and pass it our model, the grid we wish to tune over, and set CV equal to KF. This returns a grid search object that we can then fit to the training data, and this fit performs the actual cross-validated grid search. We can then print the model's attributes best params underscore and best score underscore, respectively, to retrieve the hyperparameters that perform the best along with the mean cross-validation score over that fold. Grid search is great. However, the number of fits is equal to the number of hyperparameters multiplied by the number of values multiplied by the number of folds. Therefore, it doesn't scale well. So, performing 3-fold cross-validation for one hyperparameter with 10 values each means 30 fits, while 10-fold cross-validation on 3 hyperparameters with 30 values each equals 900 fits. However, there is another way. We can perform a random search, which picks random hyperparameter values rather than exhaustively searching through all options. Let's demonstrate this approach. We import randomized search CV from scikit-learn.model selection. We set up kfold and param underscore grid, and instantiate the model as before. We call randomized search CV using the same arguments and variables as grid search CV. We can optionally set the n underscore iter argument, which determines the number of hyperparameter values tested. So 5-fold cross-validation with n underscore iter set to 2 performs 10 fits. Again, we can access the best hyperparameters and their score. In this case, it is able to find the best hyperparameters from our previous grid search. We can evaluate model performance on the test set by passing it to a call of the random search objects.score method. It actually performs slightly better than the best score in our grid search. Thanks for watching. In the next video of the playlist, we'll learn how to impute missing values, convert categorical data to numeric values, scale data, evaluate multiple supervised learning models simultaneously, and build pipelines to streamline our workflow. Feel free to ask any questions in the comments section and we'll be pleased to answer those. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.